Hello everyone, welcome to this week videos. In this week Aspen Plus tutorial videos, I'm going to simulate a very simple process, which is a process of drying of dolomite powder. And specifically, I am going to discuss the convective dryer block or dryer block for solid processing in Aspen Plus. Okay, let's begin. So as you can see here, this is our Aspen Plus design problem. In our design problem, we have a solid dolomite powder with initial moisture content of 0.2 or 20% wet base. And this solid powder has a temperature around 95 degrees Celsius. And this solid powder or wet solid powder will be dried in a convective dryer in a co-current manner, meaning that the solid dryer will enter the unit operation maybe on one side, and the flow of the heating material, in this case hot air, will also enter on the same direction, and both of the heating material and solid powder will leave out the unit operation on the other side. Basically, the flow of the material proceed on a parallel and in the same direction. And then we have the dryer length is 6 meters. That's the dimension of our dryer. And the solid will spend their time inside the dryer for 3 hours. So our task here is to calculate what is the solid moisture content leaving the dryer if we use a hot air containing water by mass fraction 0.002 and temperature of 200 degrees Celsius at the inlet side. Other than that, we also need to calculate the temperature and moisture content profile for both solid as well as the gas phase. Actually, if you ask me what dolomite is, to be honest, I do not know much about dolomite, except that I know dolomite is a solid crystalline material and it is in a powder form. The chemical formula of dolomite is a calcium magnesium carbonate dicarbonate, meaning that they has a calcium element, they have a magnesium as well as carbon and oxygen element exists in a carbonate form. Other than that, I also found that dolomite is a crystalline material, meaning that they have a long range periodic atomic arrangement in their crystal structures, and they have a hexagonal crystal. They exist in the hexagonal or trigonal crystal system. In terms of usage, they are being. I checked on an internet. I found out that dolomite has a market value around 24 to 25 billion US dollars, and they are used for a variety of applications. For example, in agriculture, where you can add dolomite to adjust the pH value of the soil. Technically, a dolomite is like a limestone. You can visualize dolomite as limestone. Other than that, they are also used in the metallurgy industry, in glass processing, and as well as they are also used in concrete, in concrete or cement production. I guess I believe there are a lot more other applications which I do not know in detail, by the way. But if you want to learn more about dolomite, please go ahead and make yourself useful by looking up the information on the internet. Okay, coming back to our design problem. Basically, we have a convective dryer. Here, this is our convective dryer. We have a solid dolomite in around 2,000 kilogram per hour of dolomite solid at 95 degrees Celsius and 1 bar pressure. And as I said, they have a moisture content around 0.2. After that, we have air coming in concurrently into the unit operation, around 10,000 kilogram per hour at temperature 2,000 degrees Celsius and 1 bar pressure. And they also contain a low fraction, a low mass fraction of water, around 0.002. And then both air and solid leaving out the dryer on the other side of the unit operation or dryer block. Another important information that we need to input, or we need to understand, or we need to at least take note is a convective mass transfer coefficient, which is 5 to the power of minus 5 to the 10 to the power of minus 4 meter per second. We also need to know what is the drying curve, how the drying behavior occurs for this solid inside the dryer. And then because this is solid, we need to know what is the particle size distribution, because different particle size distribution will have a different drying curve. And then we also need to know that moisture content of a solid phase is 0.05 by dry basis, and the critical moisture content is around 0.1 dry basis, which I will explain later on. And then here we have our particle size distribution of our solid dolomite. We have, around 20% is between 4 to 5, 20% is between 5 to 6 millimeters, around 40% is between 6 to 8 millimeters, and lastly, the remainder 20% is between 8 to 10 millimeter size. Okay, these images was modified based on these references. If you want to see what is the original figure of the from the reference, please go ahead and then look at this website. In this case, I have on y-axis is a drying rate or temperatures. On x-axis, I have time, meaning that how the time spent in the dryer. If we look at this red curve here, this is what is known as the drying rate, by the way. So at the initial period, you can see that the drying rate increases pretty sharply. The reason is because at this point, okay, there's going to be a transfer of sensible heat from the hot element or hot air into the water or solid itself. So water gain energy, and some of them has a lot of energy to transform, has enough critical energy, I would say, to phase change from solid phase, from liquid phase to a vapor phase, and then join the air stream. Obviously, when we increase as time goes, okay, there's going to be a lot more the solid, and the system itself has a higher gain in a lot of energy and has higher temperatures, and the drying rate will continue going up. And at some point, we will observe a constant drying rate, meaning that in here, okay, the liquid at the interior side of your solid need to migrate first to the surface, and then they need to they will undergo phase change from a liquid phase on the solid surface into a gas phase or vapor phase. Now, because the reason why this drying rate is constant is because the rate of migration of a liquid from the interior surface of a solid is equal from the interior surface of your solid to the surface is equal to the rate of evaporation from the surface, rate of evaporation of the liquid from the surface to the gas phase. So because they are equal, I mean, you cannot go higher. You cannot have a greater drying rate if you don't have liquid on the surface to begin with. So there's a point where the rate of liquid migrating from inner surface interior of your solid into the surface is equal to the rate of evaporation. And then after a certain time, okay, we will see a decline in the drying rate. Now, this is because at this point, there are not many liquid or moisture left in the interior to migrate to the surface, and then this liquid on the surface undergo phase change to a vapor phase, and then even though you are spending a lot of time already inside the block, because there's not much liquid to begin with, that's where you see a decline in the drying rate of your solid. And then if we see this green curve here, this green curve represents a percent of moisture content of solid, I believe, as a function of time. And obviously, you know, as the time goes, okay, from left side to the right side, as the times are becoming longer, as the solid spend more time in the dryer, obviously the moisture content start to decrease to a point where it begin to level up. And then the purple curve here represent the temperature of the air, if I'm not mistaken, as a function of time for a co-current, for co-current dryer, for the purple one, and then for this orange one, if we have a dryer operating in the counter current manner. Okay, next I'm going to show you another drying curve taken from this textbook. In this drying curve, we have a drying rate, okay, on y-axis, and then this is on x-axis. We have a moisture content of solid, and obviously at the beginning we begin with the high moisture content of solid, you know, and this represent by, and then at the initial moisture content of solid, we have a high drying rate. And then as the time goes, the moisture content becoming to decline, and then so does the drying rate. A few important, I'll say, parameter here is a critical moisture content. What does it mean? Critical moisture content means the content of the moisture in the solid when the drying rate begin to decline. And then another one is the equilibrium moisture content, meaning that the moisture content in solid that is in equilibrium with those in air. Actually, in Aspen Plus, we have a solid dryer model, and this solid dryer model capable of doing several different mode of calculation. The first one is a shortcut method. The second one is convective dryer method, spray dryer method, as well as contact dryer mode. And for this simulation, we're going to use the convective dryer method or model. And finally, this is our drying curve table that we need to input in our Aspen Plus. As you can see here, we have in this table, we have two columns. The first column is a normalized solid moisture. The second column is a normalized drying rate. And obviously from this table is a unitless. It does not have any unit. The reason is because this is normalized value, meaning that we have, if I talk about the first column, normalized solid moisture means that the solid moisture content at time I divided by the solid moisture content at time 0. And because the denominator has a unit and the top side of your fraction also have a unit divided by unit, you have a cancels out, and you have a unitless of values. And in Aspen Plus, the input information that you need to put in is in this form, by the way. I think that's all for the introduction. Let's go to our simulation. Okay, I have my Aspen Plus ready here. Let's begin. Okay, for your information, Dolomite is basically a single chemical species. However, I try to find the Dolomite material in Aspen Plus data banks, but it is not available. So what I'm going to do is I am going to specify two components, which is the magnesium carbonate as well as a calcium carbonate, and assume that these two have a 1-to-1 weight ratio. Obviously, when we talk about drying, we have water content, so we need to type waters as well as air. Okay, I'm done specifying my component. Hit next. Okay, my base method, I'm going to use ideal. And then I'm going to hit next. And then I'm going to go to the simulation environment. Okay, for dryer, you need to go to the solid tab in the model palette, and then choose dryer. Actually, I want to choose, all of them are more or less the same, but I just want to use this because the figure looks very nice, I guess. And then I'm just going to connect my solid in. I'm going to rename it later, solid out. This one, inlet gas, is optional, but I'm just going to add it anyway. And then gas coming out. I'm going to rename the first stream as solid in. The second one is solid out. Solid out. And then I have air coming in. And then air coming out. And perhaps I'm going to rename my block as a dryer. Okay, perfect. Okay, now that I'm done. Oh, by the way, before I begin, I need to set up my because I'm dealing with solid. By the way, I need to set up my specification, and then I need to choose MIXCSPID to represent the stream as conventional, non-conventional, as well as C solid with particle size distribution. Oh, I forgot to do one thing, by the way. I need to go back to properties, go back to specification. My magnesium carbonate is in a solid phase. My calcium carbonate also in solid phase. I'm going to hit next one more time. I'm going to go back to my simulation environment. And then, yeah, I already chose the correct one. So that's fine. And then I need to go to a solid. I need to go to the solid folder. Okay, my moisture component should go to this right side of your box. Okay, you can double click or you can select and then click this guy, the triangle thingy. Is it triangle or right side arrow if you wish. I'm going to adjust my PS particle size distribution mesh. My number of interval only 4. My size is in millimeter. And based on the particle size distribution that I just mentioned, I know that it begins from 4 to 5, and then 5 to 6, 6 to 8, and then 8 to 10 millimeters. Okay, I'm all set here. I'm going to hit next. I think it's going to bring me to the air in first. So my air is around 200 degrees Celsius. 1 bar pressure, the mass flow. No, I'm sorry. I'm going to use a mass flow here, around 10,000. And then I'm going to specify mass fraction here. And the air still contains water, by the way, but it is very low concentration, low water content. It's around 0.002. And then 0.998, the remainder of the fraction belongs to air. Okay, looks good. I'm gonna hit next, and it's gonna bring me to the solid in form. So I'm gonna go to the CI solid tab. The temperature of my solid stream, CI solid stream is 95 degrees Celsius and 1 bar. I'm going to use mass flow here around 2000. And then my mole flow is, no, I'm sorry, mass fraction. So it's 1 to 1, so 0.4, 0.4. And water, if you remember, is 20% by weight basis. And then I need to specify my particle size distribution. Go to the particle size distribution and then just add in your weight fraction. The first one is 20%, the second one is 30%, the third one is 40%, the fourth one is 20%. Okay, I think I'm all set specifying the process stream. Next, just hit next. Okay, here I need to choose convective dryer. Gas flow direction should be co-current because that's what's specified in the simulation in the because that's what's specified in this problem, example problem. I'm blanking up just now. I'm going to choose solid residence time and length. Length is 6 meters, and the solid specified in the example problem is 3 hours. They're going to spend 3 hours inside the dryer block itself. Okay, looks good. And then I'm going to go to the mass or heat transfer tab. I'm going to specify mass transfer coefficient, which is 4 minus 4 to the power 4 times 10 to the power of minus 4, if I'm not mistaken. No, I'm sorry. 5 times 10 to the power of minus 4 meter per second. Okay, looks okay. And then I go to the drying curve. Solid moisture content basis is, the critical one is 0.1. Equilibrium moisture content is around 0.05. Okay, you can represent your drying curve by function if you know what is your function, okay? But I'm given the data, so I'm going to input data. So normalized solid moisture content is 0, 0.1, 0.2, 0.35, 0.65, 0.85, and finally 1. And then 0, 0.1, 0.5, 0.8, 0.9, 0.95, and lastly 1. Okay, I think everything is ready. I'm gonna hit next, and I'm gonna run my simulation now. Let's see what happened. Okay, I already got my result. No warning, no error, so that's perfect. So I think I'm gonna just double click the dryer and then see the result. Go to result. Okay, if you see here, this is my outlet solid moisture content by dry basis. Previously, before it enters the dryer, it has a moisture content by wet basis, if I'm not mistaken, around 0.2. Now it has been decreased by 0.1. Okay, we got our answers. And then to create the temperature and moisture content profile for both phases, gas phase and solid phase, just go to profile. And then you can create a custom graph, custom figures, I guess. Click. The x-axis should be in length. I can choose this one for vapor phase, this one for solid phase temperatures, and then I hit OK. Okay, as you can see here, this is the temperature. It's dropping because there's a transfer of heat, by the way, as a function of length. I'm not going to discuss this in here, by the way, because I already compiled most of my result in the Excel. No, in the PowerPoint presentation. The next one is if you want to create the profile for the moisture content, just do the same. Choose vapor moisture content as well as solid phase moisture content. And it's going to take a while. So as you can see here, the vapor phase moisture content is going up. Well, obviously because there's going to be water from the solid phase being evaporated, and then goes into a gas phase or vapor phase, if you will. And the same goes with the moisture content in the solid phase. Now, in case you are wondering what will happen if I say, you know what, let's do one experiment where I'm gonna let the solid material spend around maybe 8 hours. You know what? Maybe 5 hours in the dryer. Let's see whether we can get a much lower moisture content. Okay, I'm gonna run my simulation. Okay, I'm gonna check the result. Summary. Yeah, the outlet moisture content is dropping to around 5% only. So that's good. Okay, this is my simulation result. And as you can see here, this solid moisture content at the dryer outlet, where the outlet solid moisture content by dryer basis is around 10% only. And previously we have around 20% before it enters the dryer. It has around 20% of a solid of moisture content, wet basis, if I'm not mistaken. I could be wrong, but you have to check it again. And that is the temperature profile for vapor phase going down. Solid temperatures also going down. Well, it's going to make sense because it is a it is a co-current, say, mode of drying. And then this our moisture content profile. For the green one is the vapor phase moisture content, while the purple? It's a pink. I think it's a magenta one. Magenta line here represent the solid moisture content dry basis as a function of the length of your dryer. So obviously, as they pass through the dryer, okay, they will spend around 3 hours throughout the entire length of the dryer. But upon exiting the dryer at length around 6 meters, obviously it is clear that solid moisture content, a dry basis is around 25, has been dropped to 10%. And the opposite, I would say, behavior is observed when we talk about the vapor phase moisture content. Okay, that would be all for me. Thank you all for listening. If you like the videos, give it a thumbs up. Consider subscribing to my channel, and I'll see you guys in the next video. Bye.